In our modern world, sensitive electronic components are constantly bombarded by stray magnetic fields. These fields can cause data corruption or signal noise. To protect them, we must understand how to redirect magnetic flux away from critical areas. The most effective way to protect these components is through passive magnetic shielding. By using a high permeability material, we can create a path of least resistance that guides the magnetic flux around the protected volume rather than through it. The secret lies in magnetic permeability, denoted by the Greek letter mu. Ferromagnetic materials like iron or mu metal have a much higher permeability than air, meaning they are much more conductive to magnetic flux lines. Let's examine a ferromagnetic cylinder. This geometry is ideal for shielding cables or sensors. The cylinder acts as a magnetic conduit, capturing external field lines and confining them within the thickness of its walls. As the external magnetic field encounters the cylinder, the lines of flux prefer the high permeability path of the metal wall. This process, known as flux exclusion, effectively clears the interior cavity of most magnetic influence. At the boundary, physics dictates that the tangential component of the magnetic field must be continuous. Because the material's permeability is so high, the field lines are bent sharply, becoming almost entirely tangential within the cylinder wall. Much like light refracting through glass, magnetic flux refracts when entering a ferromagnetic medium. The high permeability causes the flux to cling to the material, traveling along the circumference rather than penetrating the hollow core. We measure the effectiveness of a shield using the shielding factor, S. This is the ratio of the external field strength to the field strength remaining inside the cylinder. A perfect shield would have an infinite shielding factor. Consider a thin-walled cylinder. If the wall is too thin, it cannot carry all the flux lines without reaching saturation. Some flux will leak through into the center, resulting in a lower shielding factor and less protection. In a thick-walled cylinder, there is more material to carry the magnetic flux. This significantly increases the shielding factor. However, there is a point of diminishing returns where adding more thickness provides very little extra protection for the cost. For a long cylinder in a transverse field, the shielding factor is approximately proportional to the permeability times the wall thickness, divided by the internal radius. This formula helps engineers choose the right dimensions for their specific needs. Every material has a limit. If the external field is too strong, the ferromagnetic material becomes saturated. Once saturated, its effective permeability drops toward that of air, and the shielding effect disappears almost entirely. To achieve extreme shielding, engineers use multiple layers. Each subsequent layer reduces the residual field from the previous one. This nested approach is far more effective than a single thick layer of the same total mass. Flux can leak in through the openings. To summarize, magnetic shielding works by providing a high minimum permeability path. This shields are often made much longer than the object they protect that excludes flux from a volume, or are capped with hemispherical ends. The effectiveness depends on the material's permeability, the wall thickness, and the avoidance of magnetic saturation. Think about the formula we discussed. If the shielding factor is proportional to the thickness teeth divided by the radius, what happens when teeth increases? Take a moment to consider the relationship. The correct answer is C. Because the shielding factor is directly proportional to the thickness in our approximation, doubling the thickness will roughly double your protection, provided the material does not saturate. Generated by Vision Solve AI.